Okay.
Okay. So shall I go? Shall I go?
Yes, please, yes.
Okay. Sorry about the technological hiccup. And thank you, Lucian, and everyone else for organizing this. It's my pleasure to speak here today to all of you. My name is Bartomeu Monserrat, or Tomeu Monserrat, and I'm based at the University of Cambridge. And my aim today is to give you an overview about phonons and electron-phonon interactions. And the idea is to make it a pedagogical approach, so going to the basics and seeing where they come from and how we can calculate them. And then depending on time at the end, we can touch on some current research topics related to phonons and electron-phonon interactions. And I quite like this to be interactive, so if you have any questions or any comments along the way, then feel free to interrupt and just ask them. But before I start with that, I thought I would introduce myself so you know who I am. So I'm an assistant professor in the University of Cambridge in the materials department, and we work on computational methods to study material properties. And within that, I can see there is some issues with this slide for some reason. Give me a second. Sorry. So within that, we work on a variety of areas. So we're interested in the optoelectronic properties of semiconductors. We study electrons, excitons, phonons in semiconductors and how they affect their optical performance in devices like solar cells or LEDs. We're also interested in topological materials and trying to understand how we can describe both electron and phonon band structures in terms of topology. And more recently, we've been interested in a new direction in the topology research area, which is called multi-gap Euler topology. We also work a lot on high pressure physics, and that interest is to build phase diagrams of what happens to the chemistry and physics of materials when you apply extreme pressures to them. And these are pressures that you may find inside planets, for example. And in that context, we're also very much interested in superconductivity. And finally, the thing that underpins all of this is method development. So we write our own software to do many of these calculations. And traditionally, the software we've been writing has been based on quantum mechanical modeling. But more recently, we've also started working on machine learning, which is a tool we think can aid in our studies. I'm also very much interested in science education, and I have a YouTube channel. I co-host a YouTube channel where we teach mostly quantum mechanics at the both undergraduate and graduate level. So we have topics ranging from eigenvalues and eigenstate, as you can see there, all the way to second quantization and topics like that. And I'll refer briefly to some of these during the talk because it's relevant to phonons and electron-phonon coupling. And yeah, this is my group made of some postdocs, PhD students, and master students. And actually later today, I think you'll hear a talk from one of my postdocs, Dr. Sanwoo Kim, who will tell you a little bit more about some work we've been doing recently on superconductivity. So that's it. That's it about introducing myself, and let's go to the meat of it. And I want to start with what I call here the theory of everything. And of course, what I mean here is the theory of everything when we try to describe materials. And we can write it down pretty concisely. So this is what one may call the condensed matter Hamiltonian, with a few caveats. So here we ignore relativistic effects and so on, which could be incorporated afterwards. But beyond those caveats, this Hamiltonian here essentially is all we need to describe any material that you will ever find. And it has three main families of terms. The first one here is a term that describes the electrons. So the first summation is the kinetic energy of the electrons, and the second pair of summations represents the potential energy of the electrons, is the electrostatic interaction between electrons, so the electron-electron interaction. Then we have the second family of terms, which describes the nuclei. Again, the first term is the kinetic energy of the nuclei, and the second one is the potential energy of the nuclei, because they're also charged particles. And then finally, the third family of terms is the one that couples these two subsystems. So it couples the nuclei with the electrons, again, with a Coulomb type interaction. So in principle, this is all we need to understand any material, and indeed any chemical. But of course, the challenge is that we don't really know how to solve for this very, very complex Hamiltonian, because the number of particles can be extremely large in a typical material. But if we could, then all we would have to do is to plug this Hamiltonian into our eigenvalue equation and solve for this eigenvalue equation to determine the eigenfunctions psi and the eigenvalues E. And that would give us all the energy levels in the material, all the energy eigenstate of the material, and from that you can build any state that you're interested in, and in principle extract any sort of information that you're interested in your crystal. Now, of course, in practice, we can never solve that. It's far too complicated, even for the simplest of atoms and molecules. So we have to start finding approximations to these equations. And the basic approximation that underpins the vast majority of models that we have for materials, and pretty much 99% of all the papers you'll ever read about materials modeling are based on this, is the so-called Born-Oppenheimer approximation. So that's the starting point of everything we do. And the maths can be a bit tedious to go through, but the basic idea behind the Born-Oppenheimer approximation is really straightforward. The basic idea is that although the nuclei and the electrons in a material experience the same forces, they're all subject to the electrostatic forces, their response to these forces is very different. And that's because the nuclei are much, much heavier than the electrons. In particular, the lightest nucleus is that of the hydrogen atom, which is a single proton, and that's about 2,000 times heavier than the electron. And any other nucleus is even heavier than that. So there's this huge discrepancy in the mass of these two types of particles, and therefore applying the same force on them will lead to radically different responses. And this is the basic idea that we're going to exploit to make some approximation to the condensed matter Hamiltonian to make it more tractable than it is. And to do that, what we're going to do is we're going to, the derivation is actually not that difficult, so we can sketch it here and then you can always fill in the gaps in your own time. What we do is we consider a particular nuclear configuration. So we have our nuclei in our system, we have our electrons, and we imagine we take a snapshot of the system when the nuclei are at one particular position, and I call that capital R. And then for that particular nuclear position, we can solve for what the electrons do if we fix the nuclei at that positions. And that's what the resulting Hamiltonian for the electrons look like. So it's a Hamiltonian we had earlier, but now we've removed the kinetic energy of the nuclei because we've fixed them in whatever configuration they happen to be. So this is what we call the electronic Hamiltonian. In itself is also a Hermitian Hamiltonian, just like the original one. And it also has its own eigenvalue equation. And now I call its eigenstates little psi and its eigenvalues lambda. And again, we could in principle solve for this electronic Hamiltonian. And indeed, there are many, many methods that attempt to solve this electronic Hamiltonian. Density functional theory is one of them, dynamical mean field theory is another one of them, and so on. But then what we can do is we can notice that this electronic Hamiltonian is not quite the true Hamiltonian of the system because we're neglecting the kinetic energy of the nuclei. But in itself, it's a completely valid Hermitian operator. It just doesn't describe fully our own system. But any Hermitian operator has a very special property, which is that its eigenstates, in this case the psi, span a full basis for the state space or Hilbert space of your system. That means that in principle, we can pick the eigenstate of this electronic Hamiltonian and exactly write an expansion of the true eigenstate of the system, where we don't actually neglect this kinetic energy of the nuclei. And so that's what I have at the bottom. At the bottom, I have the true wave function on the left, and I'm writing it down as an expansion on a particular basis, which is given by the electronic eigenstates. And the way I'm writing the state of the system here is exact, because the electronic eigenstates are a complete basis of the system, because the electronic Hamiltonian is a Hermitian Hamiltonian. And so in a sense, writing down this equation at the bottom is equivalent to solving the top equation for the full Hamiltonian. And here the challenge now is figuring out what these expansion coefficients chi are when we write the Hamiltonian in this basis of the electronic Hamiltonian eigenstates. So what we can do now is we can not just write our state in that electronic basis, we can write the full Hamiltonian eigenvalue equation at the top in that basis. And I won't go through the maths, but you can calculate that. You just do it in the standard way. You write a particular operator in a particular basis by calculating its matrix elements. And if you go through that derivation, you find that the exact eigenvalue equation at the top in the red square in that particular basis of the electronic eigenstates becomes this equation, this long equation at the bottom, which has 3 lines. And again, I want to emphasize that up to this point, this equation is exact. Okay, all we're doing is we're writing the full Hamiltonian in a particular basis, but we haven't made any approximations yet to the full Hamiltonian. Okay, and now this equation here has 3 terms. The first line is a term that contains the kinetic energy of the nuclei, the eigenvalues of the electrons, and the eigenvalues of the full system. And then the second and third lines are lines that include matrix elements that mix electronic and nuclear degrees of freedom. So you can see in the middle line, we have the gradient of an electron wave function with respect to a nuclear coordinate. And in the second line, we have the gradient squared of an electronic wave function with respect to a nuclear coordinate. So going back to our very original Hamiltonian, the first line is one that describes the motion of the nuclei, and the electronic states are all captured in this lambda parameter that gives us the electronic energy, whereas the next 2 lines capture the electron-nucleus interaction. They describe the transfer of energy between the electron and the nucleus subsystems. So let me emphasize once more that up to this point, we haven't made any approximations whatsoever. All we've done is we've rewritten the original eigenvalue equation at the very top, which is in abstract form, in a concrete basis, in particular in the basis of the electronic eigenstate of the system. And now at this point is where we're going to make an approximation, because the second and third lines in the bottom equation are lines that include this exchange of energy between the nuclei and the electrons, and in particular, based on this adiabatic principle that the nuclei move much, much, much slower than the electrons, then to a first approximation, we can say that the slow motion of the nuclei will not be capable of driving electronic transitions. So this is, of course, an approximation, but it works very well if indeed the nuclei are much, much, much heavier than the electrons. And therefore, the Born-Oppenheimer approximation consists in crossing out these 2 terms. Okay, and this is the point where we make an approximation. Okay, so to make progress in materials modeling, we pretty much always make this approximation. But getting to this point is useful because if we encounter some situations where this approximation doesn't work, then we know how to improve on it, because we can just go back to this equation and uncross these terms, include them, and see what develops. And that indeed is something that's necessary when you have things like conical intersections and so on, which are features that appear particularly in chemistry, where the calculations are perhaps a bit easier because the systems are not so complex. So this is the Born-Oppenheimer approximation. And to put it in in perspective, what we can say is that we started with the full Hamiltonian at the top, and that's the Hamiltonian that has electrons, nuclei, and their interactions. And in principle, if we could solve that full Hamiltonian at the top, we would be done. Okay. In practice, we cannot solve it, so we invoke this Born-Oppenheimer approximation. And what that does, it allows us to simplify this problem by dividing it in 2 different problems. It allows us to separate this very, very complex problem into a smaller problem that only looks at the electrons, and that's called the electronic problem, and the second smaller problem that only looks at the nuclei, and that's called the nuclear problem. So the electronic problem is the one we have on the left, and that's one where we fix the atomic nuclei and then we solve for the electrons only, so the atomic nuclei that now only appear as parameters. And I guess most of the school you've learned about methods to solve this electronic problem. And these methods include things like Hartree-Fock theory, density functional theory, quantum Monte Carlo, dynamical mean field theory. There's a huge zoo of methods that people have developed and continue to develop to solve this electronic structure problem. But what I want to focus on today is the second part of the Born-Oppenheimer approximation, which is the nuclear problem. And the nuclear problem is the one on the left, and it tells us how the nuclei move in the system. And what I want to discuss today is why that problem is difficult, how we can find suitable approximations to solve that problem, and then what it teaches us about the material. Okay, and just to be concrete, what we have here is an equivalent equation that tells us how the nuclei move. So we have a nuclear Hamiltonian now, and the nuclear Hamiltonian has two terms. The first one is the kinetic energy of the nuclei, and the second one is the potential on which the nuclei move. And you'll notice that this potential on which the nuclei move at each configuration R is given by the corresponding eigenvalue of the electronic structure problem. So these two problems, of course, are, in this implicit manner, very much connected to each other. And put another way, to solve the nuclear problem, you first need to solve the electronic problem, because you need to figure out what this potential lambda on which the nuclei move is actually given by. And for that, you need to solve the electronic problem at every possible nuclear position. Okay, so I guess most of you were familiar with the Born-Oppenheimer approximation and the fact that it's the starting point of pretty much everything we do as people that want to model condensed matter systems. But it's often the case that we lose track of where we're coming from, because if we say you're working on Hartree-Fock theory, then you tend to just focus on what you're doing, and you sometimes lose track of where that formulation comes from, and the fact that it's just part of the full solution of what the material does when we probe it. And so what I want to do now is I'll assume that we know how to solve the electronic problem. And again, you can pick your favorite method to solve that. And assuming that we can solve the electronic problem, then we'll see how we can then solve the nuclear problem. And another way to call the nuclear problem is to call it lattice dynamics, because we're going to focus not just on any system, but mostly on crystalline materials, where the atoms are actually at crystallographic positions which are translationally invariant from one another, and therefore we can use some nice symmetry tricks to simplify things, just like we do for electrons. Okay, so let's say once more what this nuclear problem that we're trying to solve is. And on the left, I have the eigenvalue equation for the nuclear Hamiltonian. So we have, again, nuclear Hamiltonian acting on nuclear eigenstates equal to nuclear eigenenergies times nuclear eigenstates. And the key is that the nuclear Hamiltonian is the one shown on the right, and it has two terms. The first one is the kinetic energy of the nuclei. So it has a typical form where m alpha is the mass of a given nucleus. And then it has the potential energy surface on which the nuclei move, this lambda. It's a function of where the nuclei are, capital R, and it just tells us the potential on which these nuclei move. And this surface is typically called the Born-Oppenheimer energy surface, mainly because it comes from the Born-Oppenheimer approximation. And in general, if we have a simulation cell with n atoms in our system, then this Born-Oppenheimer energy surface is a function that depends on the positions of every single atom in our system. So we have n atoms in 3D. Every atom has an xyz coordinate, and therefore we have 3n dimensions for this function lambda. So put another way, this potential energy surface is a high dimensional function of 3n variables. And you can see how when the system size increases, the dimensionality of this function increases. And ultimately, this is the reason why the nuclear problem is a difficult problem, because dealing with high dimensional functions is hard. But not only it is hard to work with a high dimensional function, but in this case, we don't even know what the function is before we start, okay? Because at each configuration R, then to figure out what the value of the potential is, what we need to do is we need to figure out what the electronic eigenvalue at that configuration is. So if we have a big system with our atoms there, and we want to know what this potential energy surface is, what we have to do, we have to fix the atoms at some configuration R, solve the electronic structure problem, maybe using density functional theory, then move the atoms a little bit, solve it again, and then repeat that many times until we can map out what this function, what this lambda, what this potential energy function looks like. And as you can see, doing this when we have a high dimensional function of 3n variables is essentially computationally impossible, because we have far too large a space to sample, and every single configuration that we need to determine what this function looks like requires in itself a relatively expensive calculation. Even if it's density functional theory, which is perhaps one of the cheapest methods we have, it is still a certain amount of CPU time. And then if you have to do that millions of times, billions of times to map this high dimensional function, then it just becomes completely unfeasible. So this is essentially the challenge when we try to solve the nuclear problem. In the electronic case, we have a very complex Hamiltonian, and we don't know how to treat, for example, the electron-electron interaction very well. And things like density functional theory simplify that interaction by mapping it into a single particle problem. In the case of the nuclear problem, one could say that in principle, the problem is even more difficult because we don't even know what the Hamiltonian is. Okay, in this case, we can't write down the Hamiltonian because we don't know what this potential is. Just determining what this potential is in itself is an extremely challenging task. And then if we could determine this potential, then we still have to solve the problem. So in a sense, it's even worse than the electronic structure problem. So how do we go about solving this problem? So in order to appreciate how we can make further approximations to make this problem tractable, I'm now going to focus my discussion on crystalline systems. So up to this point, we haven't really specified anywhere that we have a crystal rather than a disordered system or a molecule. But now I'm going to be more concrete. And what we're going to say is that our atoms are arranged in a regular fashion in a crystal. So what we consider a number of primitive cells in our crystal where we apply periodic boundary conditions, so the usual construction in condensed matter physics. And then within this big supercell made of primitive cells, we're going to label every unit cell within it with the label P. So the capital R P vector is telling us the position of any given primitive cell in our supercell. And then within each primitive cell, we can have a number of atoms depending on the system. For example, diamond will have 2 atoms per primitive cell. So that's called the basis of the system. And then what we have then is that the location of a given atom is given by the location of its primitive cell, which is Rp, and then the location of that atom within a primitive cell, which is this tau alpha 0. Okay, so these taus give us the location of every atom in the cell, and they do that by first getting us to the cell and then getting us to the atom within the cell. But the coordinates that we'll find most useful are actually not the absolute positions of the atoms within the cell, but actually the positions of the atoms with respect to their equilibrium position. So usually the atoms in a crystal move around their equilibrium position, and the displacement from their equilibrium position is what we're going to call this U parameter at the bottom here. So U just means pick a particular atom, and U tells you how far away it's moving from its equilibrium position. So if the atom is exactly at equilibrium, U will be 0, and as soon as it moves away from equilibrium, U becomes different from 0. So this U parameter will be the most useful because in a crystal, the atoms just move a little bit away from equilibrium, and therefore this U parameter is something we'll be able to treat as a small parameter in our problem, and that will help us simplify the maths. Okay, so as I said, we make this change of variables from absolute position R to relative position U from equilibrium, and in this language, equilibrium is now given when U is equal to 0. Okay, so now we come to the key approximation when we study lattice dynamics in a crystal, which is how do we go from this very complex high-dimensional potential energy landscape to something much simpler. And again, it's based on a very, very simple idea. So again, if we have a big crystal where the atoms are regularly arranged, the nuclei are very heavy, and if you're at reasonably low temperatures, very far away from melting, say, then all the nuclei do is they vibrate a little bit around their equilibrium positions, but they don't go very, very far away from these equilibrium positions. So this suggests that we can actually describe the physics of the system at this low energy level by just looking at an expansion of the potential about equilibrium. And this is exactly what the harmonic approximation does. So we take the full potential lambda, which in principle gives us what happens to the system at any possible configuration. And then we say we're going to write it as the potential at equilibrium. That's lambda 0. Remember, u equals 0 is when the atoms are all at their equilibrium positions. And then we're going to write Taylor expansion about this equilibrium. And you'll notice here that the Taylor expansion doesn't have a linear term. The reason why it doesn't have a linear term is because the equilibrium of any crystal corresponds to a local minimum in the system, and therefore the first derivative around the local minimum is 0, of course. That's why we don't have a linear term. So the lowest order term that we have is a second order term, and that's the one I have written here. And then in principle, we could have higher order terms. Now, this equation has many indices, Rp, alpha, I, and so on. You don't really have to worry too much about them. That just notation necessary to keep track of all the cells in the system, all the Cartesian coordinates in which an atom can move, and all the various atoms that you can have in a given cell. But at the end of the day, all we're doing is we're picking an atom and then assuming that it's not moving very far away from equilibrium, and therefore we can approximate the potential in which it moves by a Taylor expansion around that minimum that we truncate to second order. So if this was a one-dimensional problem, this double summation and all these indices were just reduced to a single quadratic function. We just happen to have very many variables, 3n of them, and therefore we have to keep track of them, and that's why the equation took a bit complicated. But I don't want you to lose track of what's going on. All we're doing is we're doing a Taylor expansion to lowest order, which in this case is second order. So we truncate this expansion to second order, and that's what we call the harmonic approximation. Okay? Again, whenever we make an approximation, we can always improve on it by going back to where we made the approximation. And in this case, if we find a system where this harmonic approximation doesn't work, we can always come back to this point and say, okay, can we add more terms beyond the second order? And that would be a systematic manner in which you can extend this harmonic approximation. But again, I want to emphasize that there is nothing special about this very complex looking formula because of all the sub-indices. All it's telling us is how much energy does an atom gain when it moves away from equilibrium. And that's characterized by the curvature of the potential around minimum, and that's what the second derivative tells you. And here I have a very simple example. On the left, I have a red potential, which is rather steep. And in this case, the second derivative will be rather large. So that means that if you move the atom a little bit, you need to give it a lot of energy because the potential is very steep. Whereas on the right-hand side, I have a very shallow potential, which tells you that the atomic amplitude in this case will be much larger because it costs less energy to move a certain amount from the equilibrium. So that's really all this very complex looking term is telling us, just what is the curvature of the potential around the minimum. If you're more comfortable with sort of the mathematical name of these things, all we're looking at here is the Hessian of the potential energy surface. Okay, so in this harmonic approximation, we've decided that the key quantity is this curvature, and therefore in this expansion, the key quantity is this term in red here, which when we have 3n coordinates, then it's a full Hessian, and it requires these second order derivatives in all possible combinations of all possible directions in which you can move every individual atom. And this gives you an object that's you can write down as a matrix, where you move every single atom, every single pair of atoms in every single position, in every single direction rather. And this object is called the matrix of force constants, and that's the key quantity that one wants to determine when studying the lattice dynamics of a system in the harmonic approximation. Once we've determined this quantity, and we'll talk in a moment about how we go about determining this quantity, then how do we solve the problem? The way we solve the problem is we Fourier transform this matrix of force constants into what's called dynamical matrix. So we go from coordinates which are r and rp prime, which are the positions of the various atoms in the system, into reciprocal space, which gives us the wave vector essentially associated with that particular excitation. But all there is to it is the Fourier transform of one to the other. And once we have this dynamical matrix, then we can turn the problem into an eigenvalue problem, and the eigenvalues of the dynamical matrix are the squares of the phonon frequencies in the system, and the eigenvectors of the dynamical matrix are the corresponding eigenvalues to the atomic distortions that lead to those eigenvalues. So at the end of the day, once we've determined this dynamical matrix, we're done in the sense that all we have to do is diagonalize the matrix to figure out what these eigenvalues and eigenvectors are. Once we have these eigenvectors, what we can do is we can make a rotation of coordinates into what's called the normal coordinate system of our problem, where we go from our u's, which give us the displacement of every single atom from equilibrium along the xyz direction, to these collective variables or these normal variables, which give us the same information, but now where the displacements of the atoms are collective motions, which are related to each other by a Fourier transform. And the advantage of writing the problem in this new set of coordinates is that the Hamiltonian now becomes extremely transparent, and now we're going to understand really what we've accomplished with all these derivations. So once we write the problem in this new set of normal coordinates, what we have is that we go from our nuclear Hamiltonian in the middle, which is the original one we had, where we have the kinetic energy of the nuclei, then the potential energy at equilibrium, lambda 0, and then the second order term, which is given by the second order derivatives of the potential with respect to atomic displacements. And in principle, we have high order terms, but we're neglecting those in the harmonic approximation. And then when we write this problem in this new basis of normal modes, the exact same Hamiltonian looks like that one given at the bottom, where we now have a sum of these wave vectors q and phonon frequencies nu. And now the Hamiltonian looks like that of a simple harmonic oscillator. So we have just the kinetic energy again and the potential energy. But the key point is that in the original one, we have a double sum over r prime, also alpha prime, I prime. So that means that the second order terms have cross terms in them. The motion of different atoms is coupled to each other. Whereas in this normal mode basis, we have decoupled the different degrees of freedom. And that's the definition of a normal mode basis, where now we still have a sum over all the modes, but in every single term in the sum, there is only that one mode present. So we can now look at each of one separately, and then at the very end, add them all up together, rather than having these cross terms that we have in the original formulation of the problem. So that means that we've reduced the original problem, which is a quadratic problem, into a diagonal problem now, where each degree of freedom is independent, and therefore we just have a series of one-dimensional harmonic oscillators at the end of the day. So, and that means that not only have we now simplified the problem in terms of approximating the potential to second order, but because we've been able to then rewrite the problem as a simple harmonic oscillator, this is a very basic problem that I'm sure you've all solved in your undergraduate courses in quantum mechanics, which actually has an analytical solution. So we can actually solve this problem afterwards analytically. We don't actually need to find any approximate methods to solve the problem. And as a reminder, the eigenvalues of a simple harmonic oscillator are equally spaced and labeled by an integer k, given by the expression here in the middle. And then the corresponding eigenstates are given by a product of Gaussian functions and what are called Hermite polynomials. The Hermite polynomials are these hk, which are essentially a series of polynomials. And again, we can write both the eigenvalues and eigenstates analytically as shown here. And this means that once we build the harmonic Hamiltonian, then it's trivial in a sense to write down the solutions because we have them from our undergraduate course. This is what some of them look like. So the ground state of a harmonic oscillator at the top left just looks like a Gaussian. In this case, the Hermite polynomial is just a constant, so we just have the Gaussian. And then as you go to higher excited states, you get an increasing number of nodes in your wave function. You also get an even odd type sequence of eigenfunctions. But I'm sure again that most of you will be familiar with this sort of analytical solutions to the simple harmonic oscillator problem. And just in case you aren't, then in some of the videos that we have on our YouTube channel are precisely on this topic. So we have a whole series on the quantum harmonic oscillator, where we go over the basic theory, ladder and number operators, eigenvalues, eigenstates, and Hermite polynomials. So you can check that out. And then also a few extra things that you can do once you know you have a harmonic system, like, for example, build quasi-classical states, like the coherent quantum states. That, again, I'm sure many of you will have heard from. And these are all relevant for physics. For example, if you shine light to a system, you can actually coherently excite a phonon mode in the system, and you can then explore what sort of physics follows from that. Okay, so now that we've essentially found a strategy to solve the nuclear problem, we can actually take a step back and try to understand, why does this strategy actually work? So what we started with when we started to consider the nuclear Hamiltonian was this object at the top, and it has two terms. The first one is the kinetic energy term, which is what it is the same for the electrons. But the problematic term, or the difficult term, is the second term, which is this potential energy term, lambda n. And the reason why that term is difficult to remember is because it's a highly dimensional function of the nuclear coordinate r. So for every possible nuclear configuration in your system, that function, first of all, in order to describe every possible configuration of the system, you need the coordinates of all the atoms in your system. So if you have n atoms in your system, you need 3n coordinates to describe just the point on that function. And then to actually figure out what the value of that function is at that point, you need to solve the electronic structure problem. So you need to fix the atoms at that position and solve for the electrons, for example, using density functional theory. And then you need to repeat that many, many, many times for every possible configuration in order to map out this high dimensional function. So clearly that's impossible. We cannot do that for any material. So that's why the nuclear problem is difficult. So how have we solved this problem? By invoking the harmonic approximation. But what we do is, when we expand this function to second order and then diagonalize it to turn it into these normal mode coordinates, we end up with the Hamiltonian at the bottom. So it's a slightly approximate Hamiltonian because we're ignoring the high order terms, but we've made a huge reduction in the computational expense of this problem. And the reason for that is because now we have still 3n degrees of freedom. We haven't lost any degrees of freedom. We still have 3n coordinates in our system. But now the way they appear in the Hamiltonian is that they appear independently. So rather than having to solve one 3n dimensional problem, we just have to solve 3n separate one-dimensional problems. And it is much, much easier to solve 3n one-dimensional problems than to solve a single 3n dimensional problem, although both problems have the same size. And that's the key to the harmonic approximation. That's why we make this problem computationally tractable. Okay? So this is the key insight as to why we can actually solve for phonons in a material. We're turning a very complex problem into a sum of lower dimensional simple problems. Okay, so this is the basic background behind the harmonic approximation. And how do we solve it in practice, though? So we know now that if we could map out this potential energy surface to second order, then everything follows from there, because we can then diagonalize the dynamical matrix. We can then figure out the eigenvalues, eigenstates, and we can actually write them down analytically. But how do we, in the first instance, figure out what the second order terms in the expansion are? So put another way, we need to calculate this Hessian, or this curvature of the potential energy landscape. And we can calculate it in one of two ways. We can either calculate the dynamical matrix or its Fourier transform. And there are two main ways in which codes that you may encounter calculate this quantity. And both of them have to do with the fact that the key quantity we're interested in is essentially a second derivative. So we have to calculate the second derivative of a function, lambda. So how do we calculate second derivatives? So the first option is to use a numerical method called a finite difference. So whenever you have a function and you want to calculate the derivative of that function numerically, what you can do is you can go back to the original definition of a derivative, which is the limit of the gradient of that function as the change in the horizontal coordinate goes to 0, and you can then approximate that limit by just having a small but finite change in that coordinate. And that's all there is to it again in this case. To make it a bit simpler, what we can do is we can rewrite our matrix of force constant not as a second derivative of the energy with respect to atomic positions, but as the first derivative of the force with respect to atomic positions. And the reason for that, of course, is because the force is equal to the derivative or the negative derivative of the energy. So then we have a first derivative of the force with respect to atomic positions, and we can then approximate this derivative by a finite, what's called a finite difference. So we pick our atoms, we make a small displacement of one atom, and then we look at the forces on all the other atoms, and then we make a small displacement in the opposite direction. We look at all the forces on all the other atoms, then we plug all of these numbers into this formula, and then we get our approximation for this first order derivative of the force, or equivalently second order derivative for the energy. So this is something that we can always do. So it's a very conceptually simple approach to this. And all you need to be able to calculate the matrix of force constants in this case is a code that gives you the forces on the atoms. So as long as you have a code that does that, it doesn't matter whether it figures them out using density functional theory or Hartree-Fock theory or dynamical mean field theory, any method that you have that can give you forces, then you can straight away use this formula to also get the second derivatives of the energy, which then you can use to build the phonons. The one disadvantage of this method is that in order to do that, you need to include all the atoms in your system such that when you move an atom here, you can figure out what an atom that's sufficiently far away from it feels. And that means that you have to build supercells of your system in order to capture all this physics. And of course, the bigger the system size is, the more expensive the calculation is. So this type of approach suffers somewhat from scaling in the sense that if you want to have a good description of all the degrees of freedom in your system, then the calculations may become computationally intensive. Most of the time, they're still doable, but they're computationally intensive. The second approach to calculate the same quantity is to use linear response theory. And this approach is actually, it has some advantages, but the key disadvantage is that at the moment, the formulation that we have for this approach is essentially limited to density functional theory. So this approach is very often also called density functional perturbation theory, where we write the second order derivative directly as the linear response of the system to applying a perturbation, in this case, an atomic displacement in the system. And the formula in the context of density functional theory is given by this quantity in the middle, where you look at the second order change of the potential and also at the first order change of the nuclear density, which is one of the quantities that comes out of density functional theory. So this approach to calculate the matrix of force constants has two disadvantages if you want. The first one is that it's conceptually more complex than the previous one. The second one, which is related to this first one, is that the formulation pretty much only exists for density functional theory, and even within that, pretty much only exists for semi-local exchange correlation functionals. So if you wanted to do this for a hybrid functional, for example, again, most codes cannot do that. They don't have this implemented. But the one big advantage of this method is that it doesn't require supercells like the finite difference method. So if you have a problem where you have both methods available, then you should always go for DFPT, because that will always be the cheapest approach, because it doesn't require you to build large supercells. On the other hand, for many situations, DFPT is not available, and then you must go to finite differences. So usually when you do a project, it's always a matter of deciding what is the physics of interest in your project. If it's straightforwardly described by, for example, the LDA or PBE exchange relation functionals, then you should probably use DFPT. But if you have something a bit more complex where you may need hybrids or even beyond that, then you'll have to use finite differences. Okay, so this is just a summary of the comparison of the two methods. And again, my approach to computational methods is always use the most appropriate method for my problem. So depending on what you have, then again, you have to pick one or the other method. And this is an example of what you get at the end of the day once you've done all these calculations. So this is an example of the phonons that you get out of a very simple material, which is diamond. So diamond is a simple crystal with 2 atoms in the primitive cell. So that means you have 6 degrees of freedom in every primitive cell, and that translates into 6 branches in the phonon dispersion. I'm sure you've seen diagrams like this. It's the same type of diagram we use to describe electrons. On the horizontal axis, we have a particular path along the Brillouin zone. For example, the gamma point is the center of the Brillouin zone. And then on the vertical axis, we have in this case, the phonon frequency associated with that particular point in the Brillouin zone. So for example, at the gamma point, you can see we have 3 modes that go to 0 energy at the gamma point. These are called the acoustic modes, and they go to 0 energy because those modes at the gamma point just correspond to translations of the system, which cost 0 energy. And then as you move away from gamma, they have a linear dispersion, and the slope of those lines gives you the speed of sound in the crystal. And then at finite frequency, you have what are called the optical branches, which at the gamma point, they're triply degenerate because of the symmetry of the system. And they're at about 1200 or 1300 inverse centimeters. And they're called optical modes because they typically have frequencies that will couple to optical excitations. And you can typically measure those, for example, using Raman or infrared spectroscopy. And you can't really tell here, but this diagram actually has 2 sets of calculations. One done with an 8x8x8 Q-point grid to sample the Brillouin zone, and another one done with a coarser 6x6x6 Q-point grid, and that's just showing convergence. So you can't tell the difference between these 2 calculations because they're well converged. So in principle, just like in the electrons, you want to converge with respect to K point in your problem. In the case of phonons, you want to converge with respect to Q point in the case of phonons. And this just shows that you're converged in the sense that when you increase the size of the Q point grid, then the answer doesn't change. Okay, so this is all I want to say about phonons. What I want to do next is I want to talk about the interaction of phonons with electrons. But maybe this may be a good point to stop for a second and see if anyone has any questions.
Can you clarify a bit frozen up? Because in some papers in the literature, you are also hearing about frozen phonon approximation. That's basically the first method you presented.
Yeah, so...
Or that's different?
In essence, yes, it is. But there are various ways in which one can approach that problem. So for example, the one I presented is one where assume you don't know anything about your system. And what you do is you say, okay, what I'm going to do is I'm going to pick every single atom and start moving it around, XYZ direction, atom 1, then atom 2, XYZ direction, and so on. You do that for all atoms in your system, and you see what the forces look like in all of them. And then you end up with your matrix of force constants, and then you Fourier transform it, diagonalize it, and so on. Now, that's what I would call the finite difference method. In a sense, what people say when they say frozen phonons is occasionally, if you have a system with a high degree of symmetry, for example, and diamond is a good example of that, then very often, just based on symmetry, you can, before you do any calculation, you can actually figure out a lot of things about those phonons. For example, in the case of diamond at the gamma point, just from a purely symmetry point of view, you can actually learn that the optical phonons at the gamma point must be, you can actually determine the eigenvectors. The eigenvectors must be ones where the 2 atoms in the cell vibrate against each other. So even without doing any calculation, just by symmetry, you know what the eigenvectors must look like. So in that case, you can bypass the original step of the calculation and just go directly to the diagonalized Hamiltonian and just move the atoms along that frozen phonon and directly determine the frequency along that mode. So in that case, you avoid the step of having to diagonalize the problem. I think that's what most people refer to frozen phonons. But you can only do that if you know what the eigenvectors look like before you start the calculation. And you only do that, and you only know that if the system is highly symmetric and so on. Now, having said that, I think many people just mix these names. So you'll very often just hear frozen phonon when they mean what I described here, and probably vice versa. So I wouldn't get too hung up on that. But I think probably the best definition I would have for those is what I just told you.
Okay. And the second quick question is, how much you displace usually, or are there any?
Yeah, so this is a very good question. So this is a numerical question. So in principle, we want a derivative. So in principle, we would want the displacement to go to zero because we just want the slope at the origin. Now in practice, of course, if we try to do that, then we would get nonsense answer because the numerical noise would be too large. So in practice, what you want is you want the smallest possible displacement that you can get away with, but not so small that you hit that noise ratio. So another way to put the question is, what would happen if I try to calculate the force on an atom as a function of displacement, or the derivative of the force of an atom as a function of displacement? So if the displacement is too small, you're going to get noise. Then at some point when the displacement is small but reasonable, you're going to get a flat line for that slope, and that's your harmonic regime. And then if your displacement is very, very large, then you're going to start deviating from that flat band because then you're hitting these higher order terms that we've neglected in the harmonic approximation. So to do it properly, you would have to do this as a function of various amplitudes and check that you're in the right regime. But having said that, in practice, for most materials, you don't really have to do that because using a displacement of about 0.01 to 0.05 Bohr just gives you good answers. So we've tested that across hundreds of materials, and that's a good rule of thumb to do that.
So point one.
0.01 to 0.05 Bohr. Yeah.
I see.
So relatively small displacement. Yeah.
Okay, thank you. If there are any other questions.
Okay, so if not, maybe I can continue with the discussion. And what we want to do now is we want to think about, phonons are very interesting. That phonons give us a lot of information about the system. They tell us about, well, first of all, they tell us what is the free energy coming from the nuclei, and that has importance in terms of what is the stability of a crystal and so on. But then they also tell us about things like the speed of sound, as I mentioned earlier. They tell us about the heat capacity of the material, and so on. But most importantly, phonons are actually a platform on which you can then explore other phenomena by coupling them back to the electrons. And then this electron-phonon interaction drives even more phenomena, all the way from transport to superconductivity to phonon-assisted processes in optics and so on. So what I want to do in the second part of this is to essentially discuss how can we treat this electron-phonon problem. And in particular, what I want to do is I want to do some analogies with the way we treat the phonon problem. So to put it in the language of the Born-Oppenheimer approximation, remember that we started with the full Hamiltonian of the system, which has both nuclei and electrons. And then we said, okay, the Born-Oppenheimer approximation allows us to separate this very complex problem into two different problems. One for the electrons, and that's something you've learned in many other lectures in this school, and then one for the nuclei, and that's the one we've been discussing today. And so the question we want to ask now is, can we couple these two systems to explore this phenomena that arise due to electron-phonon coupling? And in order to do that, you don't have to, but I think a very transparent way of approaching this problem is to move to second quantization. And again, this is a topic that probably most of you will have encountered in your undergraduate classes. But in the case of the harmonic oscillator, it's pretty straightforward. You just have our original phonon Hamiltonian at the top of the slide, where we have the sum over the various harmonic oscillators. And then we can rewrite this down in terms of what are called ladder operators in the context of the harmonic oscillator. But in this case, of generalizing that to a material, this become creation and annihilation operators for bosons, because phonons are bosonic particles. And this is what I mean by my A and A dagger. And again, I guess that most of you will have seen the quantum harmonic oscillator Hamiltonian written in terms of this A dagger and A. There you may have called them ladder operators. Here they're just creation and annihilation bosonic operators. So this is what the Hamiltonian looks like, and all this Hamiltonian is telling you is So you have the 1/2, that's just the quantum fluctuation term. But then the A dagger A is essentially an operator that's also called the number operator, and essentially counts how many quanta of energy you have for that particular mode Q nu. And then you add all those quanta of energy for every given mode, and then you add all the modes with the sum over Q nu, and then you get your full energy for your system. But again, if you haven't quite encountered second quantization before, then I refer you back to our YouTube channel, where again we have a series on second quantization, and we cover all there is to it, essentially from the basic occupation number representation, then Fock space, and then we cover the bosonic creation and annihilation operators that are relevant for phonons, but also the fermionic creation and annihilation operators that are relevant for electrons. And then we learn how to write operators, both one body and two body operators, in terms of these creation and annihilation operators, and that essentially gives you the language of second quantization that is a very, very powerful way to describe condensed matter systems and beyond. So if you're serious about studying condensed matter physics and its computational implementation, that this is something you should learn more about if you haven't yet. So in this language, we can write our problem as we have it so far, as shown here, where essentially we have two terms, one for the electrons and one for the phonons, and each of these two terms has essentially the same form. You have a sum over all the degrees of freedom. So in the first case, you have a sum over all the electronic k points and the electronic bands n. And then for every such k and n, you have an operator that counts how many electrons you have. So that's the C dagger C. And then for each of those, you have a weight, which is your electronic energy for that particular state. And the phonon one has exactly the same form. You also have these phonon frequencies, which are equivalent to the electronic energy. And then you have the creation and annihilation operators in a form that form the number operator, essentially count how many quanta you have in that state. And then there's an extra caveat in the case of phonons, where you have this plus 1/2 at the end, that's just a contribution from 0-point motion that for all intents and purposes here we can just neglect if you want. And so formulated in this way, this Hamiltonian has the electrons on the one side and the phonons on the other side, so it doesn't couple the two subsystems, but it's a very compact way of telling us what we're doing when we're solving for a material. What we have to do when written in this way is we have to determine what these electronic energies epsilon are, and you determine them, for example, by solving the DFT problem or by solving the DMFT problem. And then you also have to determine what the phonon bands are, and you do that by doing what we've been discussing earlier today, which is building the matrix of force constant, diagonalizing it, and so on and so forth. Okay, so this is another way of looking at the problem. All you do is you write down this Hamiltonian and you parameterize this Hamiltonian by figuring out what these entries are by solving this complex DFT or phonon problems that we've been discussing. So in this new language, we still have the same question. How do we couple these two subsystems in order to investigate properties that have to do with electron-phonon interactions? So in order to describe that, I will now what I've said earlier about phonons is actually general. So particularly the finite displacement method is not limited to DFT. You could imagine using that for any method that you have, for example, Hartree-Fock theory, dynamical mean field theory, quantum Monte Carlo, if you have forces and so on. But now to make this discussion a bit more straightforward, I'm going to focus now on DFT. So I will assume that for the electrons, the method we're using to solve for them is DFT. Although in principle, you could see how you could use analogous reasoning to use other electronic theories that may not be DFT. So just as a quick reminder of DFT, but I'm sure you're all very familiar with that. So what DFT does is it tries to solve the electronic structure problem. And the electronic structure problem, again, as a reminder, is what I have here at the top. You fix the atoms at some position R, and then you build this electronic Hamiltonian, which has the kinetic energy of the electrons, the electron-electron interaction, the electron-nucleus interaction, and the nucleus-nucleus interaction, but the nuclei are fixed. So the nuclei appear not as dynamical variables, but as parameters in this problem. And then you want to solve this problem for a given nuclear configuration. If you just, depending on the property you're interested in, you just pick that nuclear configuration to be your equilibrium configuration. You solve this problem once and you're done. As we've seen, if you want to understand the phonons of the system, you cannot do that just once. You have to solve that many, many times to figure out what this electronic potential energy surface looks like for different values of the atomic configurations to then be able to fit a quadratic essentially and calculate the phonons. And similarly, when we calculate electron-phonon interactions, we'll have to do something similar. So how do we solve this problem in density functional theory? So what we do there is we replace the electronic structure Hamiltonian at the top by what's called the Concham Hamiltonian. And that Concham Hamiltonian has two important features that are different from the original electronic Hamiltonian. The first one is that the single particle Hamiltonian, so we no longer have a coupling between the different quasi-particles in our problem, it's the single particle Hamiltonian. And the second one is that we describe this complex electron-electron interaction in a mean field manner using a particular potential which we call the Concham potential. Here I label Ks. And the Concham potential in general has three terms. The first one is the electron nucleus potential. And that's the same as the one in the Hamiltonian above because the nuclei are fixed and we just look at, essentially they act as Coulomb sources around which the electrons move. And that's relatively straightforward to take into account. And then we have two electronic terms, which are the Hartree term, which again we can write down precisely, and then everything else that is not included in the Hartree term or the electron nuclear term, we dump into the third term, which is what we call the exchange correlation term. And that term is meant to do the heavy lifting of capturing all this subtle physics that has to do with electronic correlation. Now, as you probably know, if you've ever played around with density functional theory, we don't really know what this exchange correlation term is, and there is a whole zoo of approximations for it. The simplest one is the local density approximation. We also have generalized gradient approximations like PBE and so on. We have meta-GGAs, we have hybrids, we have all sorts of approximations to that. And with experience, you'll learn which approximations work best, for which class of problems and which class of materials and so on. But there is no definite best approximation for any given for any problem. Anyway, that's just a brief reminder of DFT, which I'm sure you're all very familiar with. And we can also write down the DFT problem in second quantized form. So again, the Hamiltonian is what we had earlier. We have the number operator for fermions and the electronic energy for fermions. And when we solve this in DFT, what happens is that our electronic energy just comes from the Concham Hamiltonian rather than from the full electron Hamiltonian. And the advantage of doing that is that we no longer have an explicit electron-electron interaction, so it's a mean field single particle problem, which is much, much easier to solve than the original problem. Okay, so what we're going to do now when we want to describe electron-phonon coupling is we don't just want to solve the electronic structure problem when the nuclei are at equilibrium. We actually want to see how the electrons respond when the nuclei move around. When we put a phonon into the system, how do the electrons respond? That's what the electron-phonon problem is. So what we have to do is we have to write down this Concham potential, not just at equilibrium, but actually when we put a phonon in the system. How does that potential change, and therefore how are the electrons affected by the phonons that we put in the system? Put another way, rather than solving the Concham Hamiltonian at equilibrium, where the U parameters of the nuclei are 0, we now want to solve it at some general U. And just like we did before for the harmonic approximation, we're just going to assume that the nuclei move a little bit. And in that way, we're going to be able to expand the Concham potential about equilibrium. So rather than just writing the Concham potential for a general atomic configuration, we just write the Concham potential for an atomic configuration as an expansion about its equilibrium configuration. And in this particular case, we actually truncate the expansion to first order. In this case, the lowest order term is not the second order term, like the one we had for the total energy when we were calculating phonons, But here we actually have the lowest order term is the first order term. So we approximate the Conchamp potential at a given atomic configuration by its linear change from equilibrium to that atomic configuration. So in this case, the quantity we need is the first order derivative of the Conchamp potential when we put a phonon in. And again, you can sort of see that we'll be able to calculate this quantity in a very similar way to what we could calculate phonons. So we can either calculate this derivative numerically or by finite differences, or we can calculate this derivative using linear response. This is the basic idea, and all that I have on this slide then is how can we massage, if you want, this expression to write it down in a more in a simpler form that we can more clearly understand. But the basic idea is this: we just look at the linear response of the potential when we put the phonon in the system. But if then, rather than putting, we can write this down both in terms of moving each atom in the XYZ direction, which is the expression I have at the very top, or we can write it down in terms of the normal coordinates that we discussed earlier, labeled by the phonon wave vector q and branch nu. And if we write them down in terms of the latter, then we have this expression at the bottom, and we can write it down in terms of creation and annihilation operators as well, as shown here. The details of this derivation are not that difficult. You just follow through the various formulas that relate these quantities, which you can do in your own time. You have pretty much them all written down in some of the slides in this presentation. But the key point is that once you've done all that, then you can write down the resultant electron-phonon interaction term in the simple form shown here. So this HEP just means the Hamiltonian, the bit of the Hamiltonian that captures the electron-phonon interaction term, and it has the following form. So it has a C dagger C. So these are the fermionic creation and annihilation operators. Then it has an A dagger. These are the bosonic creation and annihilation operators. And then you have this G here, and this G is the matrix element. So from an abstract point of view, it has the same form as the electron and phonon bits of the Hamiltonian, which have the creation and annihilation operators and then the matrix element. So what do these creation and annihilation operators give us? So the A plus A dagger is, these are the bosonic creation and annihilation operators. And this particular configuration just corresponds to for those of you who've done the quantum harmonic oscillator using ladder operators, you'll recognize this as the X coordinate. So all this is telling us is that here we just displace a phonon, say, along a particular direction. And that's a manifestation of the Born-Oppenheimer approximation, where there is still no real exchange of energy between the systems. So you move the phonons along, and the electrons follow adiabatically. Then the creation and annihilation operators just tell us, for the fermions, just tell us that we annihilate an electron at energy level n, momentum k, and we create another electron at energy level m, momentum k plus q. And then the amplitude for this process is given by the matrix element G. And the matrix element G itself, is written at the very bottom here. And it's a bracket expression of the change in the Conchamp potential when you put a phonon in the system. So again, this formula may look a bit obscure if you're not familiar with second quantization. If you are, then I guess it will be very clear. But what's important is the physical content of this formula. And all it's telling you is that you're picking an electron at momentum k and energy level n, and then that electron is scattering to a different state of momentum m and energy level n and momentum k plus q. And this change of momentum and change in energy is provided by a phonon of momentum q. So it's a process where you have an electron scattered by a phonon to another electron state. Okay? And that matrix element is just capturing the amplitude of this process. So that's the physical content of this. From a computational point of view, of course, what we need to do is calculate this matrix element. So going back to our full Hamiltonian, we have, up to now, we've had this Hamiltonian which has the electrons on the one side, the phonons on the other side. So now what we do is we add this third term that couples the two. And you can now see again how, in an abstract manner, what we're doing is pretty simple. We solve DFT or Hartree-Fock or whatever you want for your electronic structure problem to figure out to parameterize these electronic energy levels E in the first term of the Hamiltonian. Then you solve for the dynamical matrix and so on to figure out the phonon frequencies to parameterize the second term of the Hamiltonian that gives you these omegas. And that's what we've discussed in the first part of this lecture. And then we also have to solve the electron phonon problem to figure out what these matrix elements are in order to parameterize the third term of this problem. And then once you have parameterized this Hamiltonian, then you can just solve it to explore the physics of interest, be it superconductivity or transport or whatnot. So the general abstract strategy to solving the electronic structure problem is very, very similar to that of solving the phonon problem. And those two are also very, very similar to solving the electron phonon matrix problem. In each case, this is the Hamiltonian, you just parameterize it and you pick the method of choice to find these quantities that you need. So the key in this case, again, is just like earlier we discussed, how do we figure out what these phonon frequencies are? And we discussed we have these finite differences, linear response, we build our matrix, diagonalize it, and so on. Now we have to ask the question, how do we figure out what these matrix elements are in the electron phonon coupling case? So I won't go into it in as much detail as we did earlier because there's actually a nice parallel between the two. So at the end of the day, we have this expression here at the top, which involves the first derivative of the Kohn-Sham potential when you put a phonon in the system. So again, you can solve it in two ways, which are the same ways we had earlier. You can either build a supercell in your system, put that phonon in by explicitly moving the atoms and actually looking at how the Kohn-Sham potential changes, and then building this quantity. And this has the same features that it had for the phonon. It's conceptually very simple. In principle, it can be used with an electronic structure method, but the drawback is that it requires the use of supercells. So if you want many phonon wave vectors Q, then you need very large supercells in order to capture that. So that will be a drawback of this approach. Linear response is also available in this case. Again, it's conceptually more complex to write down, and it's usually only available with semi-local exchange correlation functionals, so LDA and PBE. But if your system is well described by these, then this is the method of choice because it doesn't require supercells. So again, you don't have to build these massive models in order to evaluate the quantity. So again, depending on the system of interest, what the relevant physics is, then you have to choose one or the other method to do that. But very, very analogous to what we discussed for phonons. Okay, so this is all I wanted to say in terms of electron-phonon coupling. Now may be a good point to stop to ask for questions again, and then Lucian or someone else can tell me whether I want to go for a bit more. I have a few more things I could discuss in terms of topics of current research, or we can just leave it here because we started a bit late, but it's now 4:30, so I'm at my time. So I'm happy to stop here, or I can continue a bit more if you want. It's up to you, really.
So any questions from the students?
Yes, you have a little bit more time if you want to just run over.
I think that would be great to see some applications and some.
Yeah.
Yeah.
Yeah, I can do that. But before I do that, any questions from?
So another technical question from my side. You said you move the atom in a supercell and you see the change of Kohn-Sham potential, but how can you see the change in the potential? Do you look at the change in the bands, or how do you characterize that change in the Kohn-Sham potential?
Yes. So what you really want is this matrix element.
Mm-hmm.
So there are various ways to understand that. So what this matrix element does is it describes the scattering of an electron at momentum k to an electron at momentum k plus q mediated by a phonon of wave vector q. And that's the reason for this choice, because you need to conserve momentum, right? So the phonon provides the necessary momentum to scatter from the initial electron to the second electron. So if you actually describe this process, so this is a momentum conservation. Energy conservation in practice means that these transitions are pretty much horizontal in your electronic states, because the phonon energies are typically much, much, much smaller than electronic energy. So the phonon typical energy bandwidth is tens of MeV, whereas an electronic energy bandwidth is EV. So from that point of view, you can very easily visualize this transition as sort of horizontal.
Horizontal,
in your band structure. So how does this become? What does this become in practice when you do a supercell calculation? So when you do a supercell calculation for a phonon wave vector Q, say Q is a wave vector that corresponds to the zone boundary. So it's a phonon wave vector half 0, 0, say. Then in that case, what you would do is you would build a supercell of size 2 in that direction. And what that does is that you have band folding. So the electronic bands at the zone boundary now get folded to the gamma point. So actually, in this case, the two states, your original state and the one you're scattering to, are now mapped onto the same point in the supercell that you've built.
Okay.
So then a very simple way to approximate this quantity actually is just to look at when you have this supercell and you put the phonon in, and a very good measure of this matrix element is just the splitting of those bands. So when you put the phonon in, those bands split, and that splitting actually gives you a very good approximation to this quantity. And in fact, the reason why I'm mentioning this particular approach is because that's the approach that Christian Haule and Gabi Collier actually followed in a number of past papers to calculate these quantities in dynamical mean field theory, where essentially you get you build the supercell, you get the eigenvalues, and then you look at their splitting when you put the photon.
But then this way you just get the electron phonon coupling. So for some particular points in the brilliant zone, or if you want.
So this, what I've described, that just gives you the electron phonon coupling between two electrons. So essentially, it gives you this matrix element for a particular Q, a particular K, a particular N, a particular M, and a particular nu. And then, but any method will just give you this matrix element. And then what you need to do is you need to calculate this matrix element for all possible N, M, nu, Q.
But that takes a lot
exactly,
of
exactly. And then you need to integrate over. So depending on the quantity you're interested in, then that can be more or less expensive. So for example, if you're looking at, and we're going to look at a few examples in a moment, if you're looking at things like you have a semiconductor and you're looking at phonon-mediated optical absorption, for example. So this is something that happens if you have an indirect bandgap semiconductor. Then in that case, really, the only relevant, although in principle you have many of these elements, most of them are zero, because the only relevant contribution is the wave vector that connects the indirect bandgap, and that's the one that allows you to bridge that gap and give you the absorption across the indirect bandgap semiconductor or the emission, depending on what you're interested in.
Okay.
In that case, it's very simple. Now, if you want to study something like superconductivity, then in that case, you actually have a full Fermi surface, and you want these quantities on the entire Fermi surface. And then you need many points. So then it becomes extremely difficult. And there, but even in linear response, it becomes extremely difficult. So then in that case, what you have to do in practice is you calculate these matrix elements on a coarse K and Q point grid, and then you use some sort of interpolation scheme. And the most popular one is Vanier interpolation, where people use Vanier interpolation on top of this to actually reach these matrix elements on a much finer grid that you can then use to calculate things like superconductivity. Transport is the same. So yeah, I've given you the basics of this, but the problem itself is, yeah.
I see. Yeah, I know it's very complex. Okay, thank you.
Much more complex. Okay, so maybe I can go on then a little bit.
Yes.
Just stop me when you want. This part should be a bit. It's a bit. I'm just giving you a number of examples, so it should be quite quick, and I can stop whenever because it's just a number of examples one after the other. And the first summary of examples, essentially, what I want to tell you now is topics of current research. In that, we've been able to calculate phonons for 20, 30 years. We've been able to calculate electron-phonon coupling again for 20 or 30 years. At the beginning, it was for very simple systems, and increasingly for more and more complex systems. But even now, there is still a lot of active research in the basics of phonons and electron-phonon coupling. And I just want to give you a few examples from our own work about where we are in terms of these sort of calculations. And if I start with phonons, what is of interest to us is calculating phonons beyond using the LDA or PBE approximations to DFT. Those are phonons in those approximations are really well established because they can be calculated using linear response, which is relatively straightforward and so on. But if you want to go beyond those levels of theory, then you have to resort to finite differences, which are much more complex calculations. And a lot of our work has been in trying to make those computationally simpler so we can actually evaluate them efficiently. And I just want to give you a few examples of when that becomes important. So the first one is here. So we were looking at this compound called lead dioxide. It's a well-known compound experimentally, so people can make this compound and measure stuff. And experimentally, it's known to crystallize in this particular space group, P42/MnM, so tetragonal phase. And so it's well known experimentally. So you can just get the structure from an experimental database, relax it, and calculate the phonons. And if you do that using the PBE functional, which is a very standard functional to use, then what you find is this phonon dispersion I'm showing at the right. So you can see all the phonon frequencies are positive, but near the gamma point, we have one that dips below zero, and in reality, it's an imaginary phonon frequency, which typically are represented with negative numbers. That just means that the eigenvalues of the dynamical matrix, which are omega squared, are negative, and therefore omega is imaginary. And whenever you find an imaginary phonon mode like this, what it's telling you is that the structure is unstable. If you push your system, if you move your atoms according to that phonon mode, then the energy of your system will go down. And that means that you'll find a lower energy structure than the one you have. So that means that your structure is unstable. It doesn't want to be there. It wants to lower its energy to a different structure. So, but this result from PBE seems to be inconsistent with experiments, because we were using the experimental structure, and experimentally they don't see a low energy structure that's distorted. They see this one we were calculating. So the question was, what's going on? This appears to be an instance where PBE failed to describe the physics of this system, which is well known experimentally. So what we did was we repeated the calculation using a hybrid functional. And as you may know, hybrid functionals are much more expensive to calculate than semi-local functions like PBE. And again, there is no linear response available for them, so we had to calculate them using finite differences. But we managed to, and the phonons that we find are those on the right. So we see some differences. We see, for example, that the phonon frequencies are a bit higher than for PBE. So these are quantitative differences between one and the other. But crucially, there is a big qualitative difference, which is that we no longer have this imaginary mode that we had in PBE. So this is an example where going beyond PBE when calculating phonons gives you completely different answers to using PBE. And in this particular case, it tells you, if you did phonons with PBE, it would tell you the wrong ground state for the system. It would tell you that the system has a ground state that's of a different symmetry than the one you have. Whereas if you do the calculation with HSE, it tells you, no, this system is stable and it can exist. And only the HSE one agrees with the experiment. So this is a clear example where you need to go beyond semi-local DFT to properly capture the phonons of the system. But then we also wanted to understand why PBE fails. Why does PBE fail in this case and HSE works? And it turns out to be pretty straightforward to understand why. And the reason why PBE fails is because PBE underestimates band gaps. So this compound, lead dioxide, experimentally is a very small band gap semiconductor. So it has a band gap of a few hundred MeV. So PBE, you will probably know, underestimates band gaps. So in this compound, it incorrectly predicts that it's a metallic system. So PBE will say that this compound is metallic or semi-metallic, whereas in reality it's insulating. So when you have a system with some density of state at the Fermi level, there is always a driving force towards opening a gap in the system. In 1D, that's called a pulse distortion that dimerizes a 1D chain. But similar phenomena can happen in other dimensions. Charge density waves are a well-known example of this. So what happens in this case is that in PBE, the system is metallic, and then there is a competition between the elastic energy that you gain when you distort the system to open a gap and the electronic energy that you lose when you open that gap. And in this particular case, the electronic energy that you gain wins out, and therefore the system prefers to distort to open a gap and reduce the electronic energy. So that's why in PBE you get an imaginary phonon mode. The system is metallic, but it wants to be insulating, and therefore there's a phonon in the system that pushes it towards being insulating. But when you go to HSE, then the band structure is not metallic anymore. HSE gives you the correct band structure, and therefore it has a small gap, and therefore now there is no driving force to open a gap because there's already a gap. So that phonon mode that was pushing the system to open a gap is no longer there doing that, and therefore the system is stable to start with. So this is I think this is a very subtle but very interesting application of beyond DFT method, beyond semi-local DFT methods, to understand very, very basic properties of materials, like what is their stability and how that relates to the electronic structure. And again, we could only do this because we had these finite difference, very efficient methods that we've been developing. And just very briefly, we were actually interested in this compound, not because of that was sort of a byproduct of that. We were actually looking at its topological properties. And we actually think this is the first example of a compound where increasing temperature stabilizes topological phase, in this case, topological nodal line semi-metallic phase. But that's a completely different story. The other example, which is some work that we've done actually with Lucian here in the call, is to combine DFT and DMFT with phonons. So again, DMFT is a beyond DFT method that allows us to incorporate dynamical correlations, and it works very well in instances where DFT fails, particularly in systems where you have open D and F electron shells. But again, there is no linear response to calculate phonons in that context. So again, we asked the question, can we calculate phonons in complex materials where you require to go beyond DFT, for example, with DMFT? And again, we had to resort to finite differences. And here we have an example from a recent paper we wrote with Lucian on a number of compounds where we benchmarked this method. And on the left, we were calculating the phonons for paramagnetic iron using DFT and DMFT, and we see very good agreement with experiment. We see that we can fully converge these calculations with respect to Q-point grid size. And on the right, we have strontium vanadate, which is a well-known strongly correlated metal. And again, you can see the DMFT phonons in blue. And at the gamma point, we also have the LDA phonon, and you can see there is a significant quantitative difference between the two. So again, an example where to get the phonons right, you need to go beyond DFT, and we can now do it with efficient finite difference methods. Another area that we're interested in terms of phonons is to study their topology. So most of you will probably have heard about electron topology, where you explore the topology of the bands of electrons. You can do something similar with phonons. And we've done that in quite a few compounds. I'm actually going to skip this. But essentially here I have an example of barium titanate, a well-known perovskite, the tetragonal phase, phonon dispersion on the left. And we can see many, many, many topological features in this phonon dispersion. They include Weil points on the KZ pi plane. There are 8 of them, and the reason why there are 8 is because there are some symmetries that sort of create multiples of these points. And then we also have some nodal lines or rings in red that correspond to mirror planes in this system that force band degeneracies across entire lines. And so on. So these sort of topological features that you're familiar with from electron systems, you can also find them in phonon systems. And in fact, we think they're quite ubiquitous in phonon systems, because unlike electron systems, phonon systems don't have a Fermi level. So in electron systems, you don't only want topology, but you want that topology to be close to the Fermi level, because if that topology is not close to the Fermi level, then you cannot really access it experimentally. But in phonon systems, you don't have a Fermi level because phonons are not fermions, they're bosons. So in that case, what that means is that you can actually access the entire spectrum. And in most systems we've looked at, actually, you find these sort of features across the board. So these are more examples of various types of topological features that we have in various types of phonon systems. Actually, I'll probably skip this, but in phonons, we can also do a new type of topology, which is called multi-gap Euler topology, which leads to interesting things like non-abelian braiding of phonon nodes at the bulk of the system. But I'll skip that for the sake of time. And I'll move to a few examples on electron phonon coupling next. So just like we can calculate phonons, we can calculate electron phonon coupling like I was describing. And again, this has important implications for a wide range of problems. Here I have an example. This is photon-assisted optical absorption. So when light is absorbed by a semiconductor, it induces an electronic transition across the bandgap. And light of energies of a few electron volts, which is what typical semiconductor bandgaps energies are, then has a very, very small momentum. You can just look at the energy momentum relation of light, and you see that for light of a few electron volts, it has a very, very small momentum compared to the size of the Brillouin zone. So just like we described that phonons drive horizontal transitions in a band structure, photons drive vertical transitions. So whenever you have an indirect bandgap semiconductor, you need a phonon to bridge that gap, and that's mediated by electron-phonon coupling. And this here is another example where phonons play a key role. In this case, it's not because it's an indirect bandgap semiconductor. It's actually a direct bandgap semiconductor, but this is a semiconductor with a symmetry forbidden transition. So the minimum bandgap is at the gamma point. And at the gamma point, both the bottom of the conduction band and the top of the valence band are eigenvalues that you can classify according to their parity. And the reason for that is because this is an inversion symmetric system. And then you have a selection rule. If the initial and the final state have the same parity, that transition is not allowed because the dipole operator is an odd operator, and therefore even, odd, even gives you odd, and the integral gives you 0. So this is a well-known semiconductor, indium oxide. In fact, it's a semiconductor that you have on the screens of your mobile phones because it's a transparent conductor when you dope it. But it's an indirect bandgap semiconductor, and the optical absorption spectrum experimentally is the one I show in this diagram by these dots. But if you do a naive calculation of the optical absorption, you see only this dashed black line. Now, note that this is a logarithmic scale. So there are orders of magnitude difference in the absorption from the calculation to the experiment. And the reason for that is because the direct bandgap is forbidden because of symmetry. And therefore, if you do calculation without phonons, you just get no absorption across the direct bandgap. And therefore, your absorption is what you have in this dashed line, which is much, much smaller than the experimentally observed one. Now, the moment you put phonons in, they enable these nominally symmetry forbidden transitions. And you can understand that in various ways. For example, in a real space picture, when the phonons move around, they dynamically break the symmetry of the system. And therefore, you no longer have these well-defined parity eigenvalues, and therefore that transition is allowed. If you want to understand that in a perturbation theory picture, then you have a second order process, and the phonon allows you to go through an intermediate state that allows, again, that transition to occur. But one way or the other, if you do include the electron-phonon interaction in this optical absorption experiment, you can see that your absorption near the band edge increases by orders of magnitude, and it becomes much, much closer to what's observed experimentally. And you can do that as a function of temperature, and then you see the temperature dependence in this absorption. Now, there is still a small difference between the calculated one and the experimental one, and we attribute that to defects. So actual static point defects in the system can also mediate this transition, and that probably explains the still somewhat disagreement, the extra bit that we need to get fully on top of experiment. But we have the intrinsic absorption, if you want, purely due to electron-phonon coupling. You can also do something similar with exciton-phonon coupling. That's something I haven't discussed at all, but just like you can solve the electronic structure problem for independent quasi-particles, you can also solve it for the electron hole problem, where you create a photoexcitation and then the electron and hole bind together to form an exciton. And then that exciton can, again, that's, if it combines, you get luminescence and so on. And that exciton can also form through indirect bandgap semiconductors. And this example here is one such semiconductor, hexagonal boron nitride in 3D. And experimentally, you see emission even through this indirect bandgap. And again, we can reproduce that only if we include the phonons in the system that mediate the momentum difference between the electron and the hole that allows you to recombine those two components of the exciton. So this is, again, something that we can do with this sort of calculation. And this is all I wanted to discuss. So here I have a few resources if you want to learn more about these topics. So at the top, I have some references for lattice dynamics. The first one is actually a very, very old book from 1954, but I still think it's one of the best books that there is out there in terms of understanding phonons in crystals. It's called Dynamical Theory of Crystal Lattices by Huang and Born. These are two very well-known people in the field. And I really recommend that book if you really want to understand phonons. There is everything you pretty much need to know about phonons in that book. And then if you want to learn more about how they are calculated in practice in more modern terms, then there is that review of modern physics paper from 20 years ago by Baroni et al., which I also recommend. And then in the case of the electron phonon coupling problem, there is again a RefModPhys review by Feliciano Giustino from a few years ago on the FPT, and I actually wrote another review a few years ago as well on using finite differences for electron phonon coupling. So again, if you want to go in detail through some of the derivations we've discussed today and see a bit more of the scope of this type of studies, then I recommend all of these references for you to pursue. And I'll stop here for good now. So thanks, and let me know if you have more questions about either the applications I've discussed or more of the topics I've discussed earlier.